The arithmetic coding algorithm we've been discussing so far is really just a special case of the algorithm when you're using a very simple probabilistic model of the source, namely an i.i.d. model. But a beautiful property of arithmetic coding is that it can be coupled with essentially any probabilistic model of the source. It basically treats the model as sort of a black box, and you can plug in whatever model is most appropriate for your situation. So how does this work? It's actually quite a simple extension of what we've done so far. So up to now, we've been assuming the following probabilistic model on sequences. So we have, for a sequence x1 up to xk terminated by 0, we said that the probability of that, we called it p star circle, was just the product of the probabilities of the individual source symbols in that sequence. So px1 times px2 times px3 up to pxk, and then p0 for the end of file symbol. So just as a reminder, we're always assuming that we have our source alphabet and we're just numbering it 0, 1 up to n, and we have some probability mass function on this source alphabet p. So those are these p's here. And we're interested in encoding sequences from x that don't contain 0, because 0 is the end of file symbol, except at the end, and they're terminated by a 0. So we called this set of valid messages to be encoded, this x star circle thing, and this was all these sequences, x1 up to xk, then 0, where each xi was in our source alphabet but was non-zero, and k is just some non-negative integer. So this is a set of all these finite length valid messages to be encoded. And this p is a PMF on this set. All right. Now, this probabilistic model right here, this is a sort of i.i.d. model, but it's a very simple model. And it doesn't really accurately reflect real world sources. So real world sources such as, language or images or audio or video, or the things that occur in the real world, they are very structured, and usually there's going to be lots of dependencies, very interesting dependencies between the different elements in the sequence. You can just think about like language. You can oftentimes predict the next letter from the previous letters. And this simple i.i.d. model does not account for that at all. So for a real-world source, this is not going to reflect reality, and as a result, you're not going to get very good compression because your model doesn't reflect the true distribution of the source. So what can we do? Well, let's think about, say there was some other distribution. Say we think that the source comes from some other distribution, Q. Maybe it's actually from Q, or maybe Q is just our model of the source. And Q is going to be some more descriptive, more interesting model than this i.i.d. model. So any distribution like this can be factored as the probability of the first symbol, x1, times the probability of the second symbol, x2, given x1, times the probability of x3 given x1 and x2, and so forth, probability of each one being dependent on the previous symbols, up to xk given x1 up to xk minus 1, and then we need one more for the last termination symbol, 0. Probability that xk plus 1 equals 0, given that all the previous ones were x1 up to xk. This just follows from the definition of conditional probability. For example, qx2 given x1 is just q of x1 and x2 divided by q of x1. So if you plug that in, the q of x1 cancels, and so forth. Do that for the same thing for all the other ones, and you can derive this identity. This is sometimes known as the chain rule for probabilities, but something which is a little bit different in this context is that it's over variable length sequences. So it's a little bit different, but it still works. So to be precise here, since these are different conditional probability distributions, to be precise, I should annotate these q1 of x1, q2 of x2 given x1, q3, and so forth, qk plus 1. So for any arbitrary model that you might want to use, you could factor it in this way. And now note that there's a very natural correspondence between the factors of this distribution and the factors of our good old i.i.d. model, right? We can just line them up here. x1 with x1, x2 with x2, x3 with x3, k with k, and the last guy, the end of file, with the end of file. So that's pretty interesting. And now let's think about what was it about this i.i.d. model that allowed us to get so close to the entropy with arithmetic coding. Remember when we were examining the near optimality of arithmetic coding under this model of the source, we were able to get within 2 bits of the entropy on average for the whole encoded message length, for the expected message length, encoded message length. So what was it about the way we did the algorithm and this model that made that work? Well, if you think back to the argument that we went through, the proof we went through, the key thing, if you look back at it, I'll remind you here, was that the length of the final interval from A to B was exactly equal to this probability right here. It was exactly equal to this P star. So if we were, the AB corresponding to this sequence, which we could abbreviate by X, was just exactly this product of probabilities right here. And that was the key. So that was the key property that arithmetic coding had. The way we've been doing it so far. So can we get an analogous property for this new distribution, this sort of interesting and maybe better distribution for whatever problem we happen to be using? So the analogous thing would of course be we would like to get b minus a equal to this q of x, or so I'm using x for this thing right here. So q of x, in other words, q of x1 up to xk terminated by 0. So can we somehow adapt the algorithm so that we can get this property? Well, let's think back in the i.i.d. case. So here was our example 1, good old example 1. And let's think about what was it about the way we did this that made it so that the width of that final interval, the length of that final interval, was exactly the product of the probabilities. So for example here, right, it ended up that the width of the interval from A to B was P2, P1, P0, and that was the sequence we were encoding. Well, the reason why was because we were subdividing according to P, right? So the reason why it had this P2 here was because that was the height of this chunk, the first chunk that corresponded to 2, right? Because we got that P2 for that first chunk that we chose, and then on the next step we subdivided according to P yet again, using the same P. And so this one, the P1 right here, this P1, that came in because, we 1 was our next symbol. And so we chose the 2, 1 chunk. And the 2, 1 chunk had height P2, P1. And then again, the third symbol, or the third factor, the P0 came in because our third symbol was a 0. And yet again, we divided according to exactly the same P right here. We divided the 2, 1, subdivided the 2, 1 chunk according to the same P. And so that was why. So that was why it always ended up that the width of that final interval from A to B was exactly the product of the probabilities in the sequence. So how could we modify this so that the final width is equal to Q? So back down here. So what we'd like to get is the final width equal to Q, and Q is the product of all these factors right here. So by analogy with with the i.i.d. case, we can just so we can just sort of see what we ought to do. This q1 is playing the role of px1, and this qx2 given x1 is playing the role of px2, and so forth. So what we should do, it's pretty clear. We should just, instead of subdividing according to p at the first step, we subdivide according to q. Well, I could put q1 x1 for the distribution of that first guy. And then we subdivide according to, well, I guess we don't subdivide. Well, I mean, okay, technically we subdivide according to q1, because I shouldn't put x1 since x1 is 2. But, the usual thing to do to denote that whole distribution is q1 x1. And then, so at the first step, we subdivide according to this distribution on the first symbol. And then after having chosen, 2, then we would say, okay, subdivide the next thing according to qx2 given x1. And now x1 is 2, so we know that we're going to be in the 2 chunk. It's not necessarily going to be the same as the way we subdivided here. It's going to be some other, crazy subdivision. So maybe, I don't know, maybe the q1 was something like, maybe it was something like this, something like that. And then qx2 given x1 was maybe something completely different. Maybe it was like, I don't know, it was like this or something. And then, so after subdividing that and then choosing the 1 chunk, then we would subdivide at the next step according to q3 x3 given x1 and x2. And we would keep on going, subdividing according to the conditional probability distribution for that symbol given the previous symbols in the sequence that we are encoding. And then at the end, once we hit our end of file symbol, the width of that final interval is going to be exactly the product of the probabilities for the symbols that actually occurred in our sequence. But now it's these conditional probabilities, not the p's. The p doesn't even exist now anymore. We're just using this new distribution q. So that's it. So that gives us exactly the property that we wanted. So all we have to do is, instead of subdividing according to p at each step, we subdivide. So at the ith step, instead of subdividing according to p, we would subdivide according to q sub I of xi given x1 up to xi minus 1. And that would give us this property. So let me write down. So what do we need in order to make this actually work? So let me write down. There is the main thing that we need out of this q. You can't just really choose any q. That's why I kept saying essentially any q, because we need to actually be able to compute those conditional probabilities. So need to be able to compute, because we're going to have to compute those in order to subdivide the intervals. Compute the conditional probability xi given x1 up to xi minus 1 efficiently or easily in a computationally efficient manner. But granted that we can do that, all that we have to do is at the ith step, so I'll write it here, at the ith step, all you do is subdivide, just what I said, subdivide according to q, this thing right here, q xi given x1 up to xi minus 1 instead of p. Instead of p. So, it's not necessarily going to be the case that you can always compute these guys easily. Sometimes, you might have a model that's easy to define, but for which it might be sort of difficult to do this kind of inference. So this is not a slam dunk that you'll always be able to do that. Okay, but granted that you can, assuming that you have chosen a model for which you can do that inference, then this is how you do the encoding. So it's just a trivial modification of the previous algorithm that we described for the i.i.d. case. And so that's how you encode. So how do you decode? Can we still do the decoding? So let's think back up here to how you would do decoding with this type of situation. So for encoding, we subdivided according to q1, q of x1, then q of x2 given x1, and so forth. And then, well, I didn't mention this, but probably, no, hopefully clear that after that, after you get your interval from a to b, then this part is just, part b is just the same. You do all of this exactly the same. You choose, the smallest binary interval that's completely contained in the interval from a to b. None of that is different. But for decoding, how do we do decoding? Well, let's think about it. So for decoding, we have our interval here from a, not from a to b. We don't have that one, but we have the purple interval here. We have this sequence, and we compute this number, z. And so for decoding, let's see, what can we do? Well, we'll just do the same thing. We subdivide according to q of x1, and if z is in, whatever chunk z happens to fall in, we know that that was the first symbol. And then we subdivide that chunk according to q of x2 given x1. And that at that point, we know what x1 was, right? Because we already decoded that symbol. So we can compute that conditional probability. That is a key fact. You already know at this step what q of x1 was. This is something which is different than the i.i.d. case. We need to know what x1 is in order to compute this conditional probability. And we do. Everything is golden because we've already decoded that first symbol. So we can compute this, and then so forth, and then so on and so forth. Then we're off to the races. You choose the chunk corresponding to the chunk that contains that number, and then that was your second symbol, and you compute the next conditional probability. You choose the chunk that contains the number z, and you keep going until you hit your end of file symbol. So decoding is just the same, works just the same way. All you have to do is modify the original algorithm to subdivide according to these conditional probabilities instead of according to p. So that's it. That's how you do arithmetic coding with a, basically arbitrary probabilistic model of the source. It's just remarkable. I mean, essentially for free, we can generalize this algorithm and be able to exploit very sophisticated probabilistic models. And this is really important because, real world sources, if you're using a model which doesn't reflect the actual distribution of the source, then you're not going to get very good compression. Like, especially, if you're using an i.i.d. model. Well, I mean, any model that you're using. If it doesn't reflect the true distribution, then you're not going to get good compression. On the other hand, the better that your model does reflect, I mean, in the real world, you're never going to actually know the true distribution. But the better that your model reflects the true distribution, the better your compression will be. On average, of course. So this is a very powerful property of arithmetic coding. And when you couple this, I mean, when you think about that you have this property, this very, ability to handle very general probabilistic models, along with the fact that you're nearly optimal for encoding the whole message and with near ideal compression, near ideal expected length, and couple that, again with the fact that this is a very efficient algorithm, it's kind of hard to imagine something which could be better. So it's quite powerful. All right, so there's one more thing I'd like to mention about this type of model, and that is with respect to the end of file symbol. So I mentioned that instead of using the end of file symbol convention, another alternative was to just encode the length of your original message. So you would encode like, K or something like that instead of having this 0. And then put that in a header or something. And that was an alternative to using the end of file symbol. But if you use the end of file symbol, then an advantage of that approach is that when you have a model of this sort, you can actually predict the end of file symbol. So think about, so remember here we had this factor that was saying what is the probability that the next thing is going to be the end of file symbol. And if you can predict when the end of file symbol is coming, maybe not, you're not actually predicting it, but you're adjusting your conditional probability distribution. And if you can, if your probability distribution is accurately putting more probability mass on the end of file symbol when it's more likely to actually occur, then you're going to get better compression than you would if you were just encoding the length of the message. So encoding the length of the message is essentially what you're essentially doing, if you think about it, is you're essentially using a probabilistic model of the length of the message by in essentially you're assuming a very particular probabilistic model of the length without paying any attention to the actual content of the message itself. But if you use an end of file symbol, you can actually look at the content. This is all the stuff that you've seen so far, x1 up to xk. And the content can help you predict when the end of file is coming. So let me just write that note here. So can predict end of file to get better compression. Than if encoding length. If encoding length. So just to illustrate, I think you probably get the idea, but just to briefly illustrate an example of that, think about if these messages were, say, emails or something like that. Then, at the end of an email, I mean, oftentimes people write particular things, like maybe a period. Maybe if you see, there's some text, whatever it is, and then a period. Well, that's, there's probably a higher probability that the end of file symbol is going to come after a period. It doesn't always come after a period, but you might adjust your probabilities. Or another example would be, like if, at the end of an email or something like that, you have a couple, line returns, and then maybe someone, then they write like bye or something like that, or goodbye or something, and then some unknown, some characters in here, like name or something like that, the person's name, and then you might expect the end of file symbol to be coming soon. So those are just a couple examples of how you could, sort of, just to illustrate what I mean by this. All right, so that's end of file. Oh yeah, and one other thing I should mention is just to illustrate, just really briefly, some examples of models Q that you might actually choose. So just a quick couple examples of Qs that you could choose, just to sort of spark your imagination. So you could use, for example, a very simple one would be a Markov model. So you might model Q x1 up to, or not the whole thing, but you would say Q xi given x1 up to xi minus 1 would just be some transition probability. Maybe you call it t xi minus 1 to xi. Or more generally, you could have some, like mth order Markov, mth order Markov model. And then, similarly, instead of just depending on the last guy, you would have some probability that depends on the previous m guys. So that's just a couple examples of Qs that you might choose, simple examples of Qs that you might choose. All right, so that is how you do arithmetic coding with more general non-i.i.d. probabilistic models of the source.